All right, so we're going to do 6.4 and then I think it was 5. The distribution of natural energy resources and then nuclear power today. So we're kind of covering all of the ones that we would consider non-renewable, at least to some extent. So we've already talked about how we like use the energy from coal and natural gas. And then this is just showing you how these things are distributed. So the concepts that they want you to be able to remember is like where they're going to occur. And then also understand that the global distribution is not uniform and it's going to depend on the geology. Within each section, so if you go back up in the notes, I told you where it was. So like petroleum is most common here. And I did that for each of the things. This map is showing us coal distribution. So this is around the world, not just the like major countries. And then here it's showing us oil and natural gas. You'll notice that they're kind of similar. That's because the same type of rock layers that are going to hold coal are going to hold the natural gas. So you have a lot of Africa where it's been unexplored, so outside the scope of the report. And some of that has also been unexplored for coal. We just don't have very good data on like where. But places that have been explored and that have a lot of these resources are going to be the US, Canada, China. Russia has a lot of the coal. We don't have good data on their natural gas and oil information. And of course, we know that there's a lot of oil in the Middle East, but it is outside of the scope of the company that put this together or the environmental group that put this together. They don't have that data. So we know that there is oil and natural gas in Russia. We know it's in the Middle East. We just don't know exactly where. Yeah. Uh-huh. So could that be possible? So it can, probably in places like Costa Rica it is. You'll notice there's a lot here that's unexplored as well. In the Congo, there's not as much that is protected, but there's a lot that it's very hard to get to, especially because of different diseases that are endemic in that region, things like Ebola and malaria. That are going to be kind of a dissuading factor for people going in and trying to like find stuff. Also, to take down all of that forest would be an environmental nightmare and a PR nightmare right now. So I think that that has a lot to do with it, that the public relations aspect of tearing down all of that remaining forest would be horrible. All right, so now we're going to talk about nuclear. When we talk about nuclear, it's generated through fission, not fusion. This is where atoms of uranium-235, which are stored in a fuel rod, are split into smaller parts after they are hit by a neutron. So you're breaking apart a uranium atom into 2 smaller atoms. This releases a large amount of heat. That heat generates steam, and then the rest of the process happens exactly like this. Okay, so you're generating the heat, which you can use that to make steam from water, and then the rest of the spinning the turbine and stuff is the same. All right, so we're just gonna, these are the kind of things you'll need to know. So we've got some half-life information. We've got that it is non-renewable because uranium is not a renewable resource. And then we have a couple of the disasters that we want to talk about. So 3 Mile Island, Chernobyl, and Fukushima. And a little bit more on half-life. And we'll kind of talk about half-life when we do math today as well. Okay, so nuclear power is often rejected because of concerns about dangers. And that's the video we're going to watch today, is about these like dangers. There are a couple different categories, like you can have a nuclear accident. There's also radioactivity associated with the waste products, and of course, weapons. Because of nuclear weapons, people are hesitant to use nuclear power. Fission, already kind of talked about that. You use a neutron to strike a large atomic nucleus and break it. The most common one we use is uranium. So you have 1 uranium, 235 uranium plus a neutron, and you get, there should be a little arrow here. There we go. You get a barium and a krypton plus 3 neutrons. Those 3 neutrons can then continue the chain reaction. So in a nuclear power plant, I think I have a diagram somewhere. Nope, I guess I don't. Let's look up a diagram really quick. Okay. So here's a good one. I think I've used this one before. Yeah, okay, so in this diagram, you can see that you have the fuel rods. These are those are your uranium. And in between, you have control rods. The control rods can be lowered to absorb some of those extra neutrons to keep the reaction going, but not too fast. So you want the reaction to continue. It's kind of a chain reaction because here we are producing more neutrons that can be used to break apart more uranium. But we don't want the reaction to go so fast that we have basically a nuclear explosion, okay? That's what we talk about when we talk about the like core melting. It's not exactly the same as the explosion we would have seen in like a weapon, but it is a very bad day. Nuclear power plants work by using heat to heat the water. The water produces steam to turn the turbine, which turns the generator. That's what we see here. So here is our water tank. We've got this heat exchanger where the heat is going to come through here into the water, heat it up into steam, turn the turbine, and then we get our electricity. So same process as like a coal burning power plant. I've already talked about the fuel rods and the control rods. So the control rods will just absorb the excess neutrons to slow down the reaction. Fuel rods are actually the fuel. And the nuclear ore, this is like the uranium that is pure enough that we can use it for this purpose. So large commercial uranium mining is found in Australia, the western parts of the US, and parts of Canada. 70% of the electricity generated in France comes from nuclear power. It has wide use also in Lithuania, Germany, Spain, the UK, Japan, China, and South Korea. The US, we get 20% of our power, of our electricity from nuclear. Currently, there's 104 plants in the US. So for the most part, people think we don't use nuclear power very much because we think of it as being dangerous. But in reality, while there have been these really big disasters, there's a lot of good things about nuclear power as well, because we're not producing any pollution at the site, at least not air pollution. We do have the next thing we're going to talk about, radioactive waste, to worry about. Yeah, we'll talk about Yucca Mountain in just a minute too. Yeah. So radioactive waste, this is once the nuclear fuel cannot produce enough heat to be used in a power plant, it still continues to emit radiation. It still is radioactive. That radioactivity can cause major problems to living things. Radiation poisoning can cause everything from like skin damage, cancer, vomiting, bleeding, open sores, and eventually death. Like if anybody watched the HBO show Chernobyl, you kind of saw some of those things. Like radiation can cause severe acute illness that ends in death, or it can cause more long-term chronic problems. The high-level radioactive waste, this is the fuel rods, and then there's also low-level radioactive waste. And those are things that are used in the process of the like functioning of the plant, but that are not like pure uranium, right? So these are the protective clothing, tools, rags, any other items used in plant maintenance. They still have to be disposed of because of their radioactivity. So they have to be disposed of properly. Uranium mine tailings are the residue left after uranium is mined. So this is even a waste product, not from the power plant, but from the mine. So we have a couple different types of waste, a couple different sources of waste. All of it, though, has to be stored in special, highly secure locations because of that danger of damage to living things. You cannot burn it. You can't dispose of it using chemicals. You can't shoot it into space, although some people have suggested shooting it into like the sun or just into space. You can't dump it on the ocean floor. It remains a threat for 10 half-lives. That's the accepted number by scientists. And the half-life of uranium, I can't remember off the top of my head. I was gonna say, I think it's something like, yeah, billions of years. So yeah, it's a long time. It's a really long time. If you're talking about uranium-234, which is not exactly the one we use, usually we use 235, it's only 25,000 years, but even that, if you're talking 10 half-lives, you're talking 2.5 million years, right? 25,000 times 10, yeah.
So essentially, like, the main problem with nuclear energy is not the energy itself, it's like what to do with stuff afterwards.
Yes.
Also, I could see the problems with like other, I guess, like other things, but like I know that space junk is a problem. If you shut it, figure out a way to like have outside the planet
So the worry with shooting it into space is that you would have a disaster on the way out. And then you would cover the planet in a nice sprinkling of radiation. So yes, you could theoretically like go put it on the moon, but you have to get it to the moon safely. And right now people are concerned about that aspect, because if you had a disaster, like if you had like the Challenger kind of disaster, or SpaceX just had a rocket that blew, if you have one of those things happen, bad news, because you've got, instead of just little pieces of space shuttle, you have radiation raining down across a large swath of the planet. Yeah. So yeah, you're right. You could, like, shooting it into space, we could theoretically like take it to an off-planet location. It wouldn't be good to leave it like just floating in space. But like some people have suggested like, well, go take it to like the moon, or take it to like send it to Mars or something like that where we're not. But yeah, that leads to other problems. And actually that would be 250,000 years, not 2.5 million. I was off by an order of magnitude. I guess it's still early. So all this waste has to be stored in special secure locations. And basically what we have come upon right now is that each plant will store it usually on site or near site in a secure like tank within a tank within a tank. If you've ever seen Emperor's New Groove, it's kind of like Yzma's plan to kill Kuzco. They like put him in a box, in another box, and then except the smash it with a hammer part. You wouldn't want to do that to the nuclear waste. All right, so we're going to talk about calculating half-life later, but basically if you calculate half-life, you're just going to figure out how much is left based on how much time has gone, and it would be like if it's one half-life period, so if the half-life is 5,000 years and it's been 10,000 years, you would have a quarter of the original material. So it would just be like 1/2 times 1/2. All right, so Yucca Mountain is the current disposal location that has been suggested. In 78, the US Department of Energy began examining the site in Nevada because there's not a lot of people that live there. They think that it would be a good site because there's not like a lot of living organisms either, like it's the desert. In 2006, the DOE released a report confirming the soundness of the site, but a few years later, the project was canceled because there are still some questions about whether the site is actually sound. So the Yucca Mountain is this suggested storage site to put everything in one place. But there's a number of reasons why people are not necessarily gung-ho about this. First, you have to get the nuclear waste to the site. How you're going to do that is going to cause possible damage, possible like destruction of environmental areas in transport. That's what we see with like oil. Tanker trucks spill and then you get oil spills, right? The same thing could happen if you had like a truck taking waste from a nuclear power plant in Northern California to Nevada. or even worse, from Connecticut to Nevada, where it's got to cross a huge swath of the US. In addition to that transportation thing, they're worried that the site itself is not necessarily the best. Yucca Mountain is relatively geologically stable, but there are some like geologic earthquake kind of activity in the area, or nearby areas that could shift rocks in Yucca Mountain if we had like the big one that we talk about happening in California. So even though it's not super close, there is some worry that like if we had a really bad earthquake, that it could damage this site. All right, the other thing that people are interested in right now is nuclear fusion. Now this is what the sun does and other stars. This is where you take lighter nuclei and force them together to make a heavier nucleus. So like a hydrogen plus a hydrogen, you get a helium. Because they each have, you know, the one proton, you fuse them together, and now you've got two protons in the nucleus. Fusion is a promising, unlimited source of energy in the future, but so far scientists have had difficulty containing the heat. So far, it is a process that is theoretically possible, but not physically possible for us to use at the moment. All right, the disasters you should know. College Board wants you to know at least these three. So 3 Mile Island. 3 Mile Island is a partial reactor meltdown in Pennsylvania. This happened in 1979. Cleanup ended in 1993. It cost about $1 billion. Epidemiological studies showed that the area had a small, statistically non-significant increase in cancers. So what that means is that the increase was small enough that they were not 100% sure that it was caused by 3 Mile Island, but it was because it was non-significant. So it didn't have the, it didn't meet what we call significance in science, where we are certain that what we're seeing is because of the thing we're talking about. Now it could be that this small increase was caused by 3 Mile Island, but because it was statistically non-significant, we can't confirm that. We are not very sure, basically. Does that kind of make sense? Okay. This is really the disaster in the US that got the anti-nuclear movement activists to try to decrease the use of nuclear power. This is the one that scared a lot of people because it happened in the US. It happened with relatively good equipment. It happened in a place where people were allegedly following safety guidelines, and so people were more concerned than when we heard about Chernobyl. Now, Chernobyl probably scared a bunch of people too. It happened a little bit later in '86. The explosion killed 134 staff were hospitalized with acute radiation syndrome. 28 died shortly after. And there were 14 radiation-induced cancer deaths that happened in the next couple of years. This was a complete meltdown of the reactor. It happened in northern Ukraine, and the enclosed area, the area there is still basically not accessible by people. We call it a radiation sarcophagus, where we're just trying to keep the radiation in that spot. It had to be further enclosed in 2017 because of leakage from that original enclosed area. So that original concreted off area that they were trying to enclose the radiation was leaking. Cleanup is scheduled for completion in 2065. So this is not a insignificant meltdown. This meltdown is the worst nuclear disaster in history. Part of the problem with this, and part of the reason why a lot of the US people were not quite as concerned, is because the reason for this meltdown was likely due to not having the proper fail-safes. In nuclear power plants, remember we have those control rods. They want to make sure that those control rods, at the first sign of a partial meltdown, at the first sign of too much heat, those control rods are supposed to slam down and stop the reaction. Part of the problem with Chernobyl was that kind of stuff didn't happen automatically. So I think that that's one reason why people in the US were more concerned about 3 Mile Island, even though it was not as bad of a disaster, because it showed that we could still have accidents even when we were following all of these rules and regulations. Fukushima is in Japan. This one you guys may remember because it was in 2011. This was induced by a tsunami. So big giant wave came in, and the active reactors were shut down, or active reactors shut down fission due to the tsunami. So the active reactors were kind of stopped, but the generators also shut down and they couldn't help with cooling. Cooling still needs to happen even if the reactor is off because you still have residual heat. So that was the problem here, was that the tsunami brought in all of this water and it flooded the area with the reactors that kept the cooling apparatuses online. Radiation in the atmosphere caused a large evacuation zone. 154,000 residents were evacuated. There was some radioactive water released into the Pacific Ocean. Screening people for thyroid issues after has found some. Thyroid issues are common after radiation because your thyroid gland is especially sensitive to some of these radioactive compounds. They found just under 200 cancers of the thyroid in children from the area. It is still unclear if this is really an increase. The rate may be due to the intense screening instead of due to an actual increase. So we may be seeing an increase in numbers of thyroid issues because they are testing the kids more often. If they were going to do this as like a really rigorous study, what they should have done was test a bunch of kids in this area in Japan, in this prefecture, but also test a bunch of kids in like Ohio or Montreal or something like that to compare. Because if it is due to intense screening, you would think that you would see increased rates of thyroid cancers in children in an area that was experiencing intense screening but had not experienced the radiation. 2 papers have shown that it was due to radiation. A third paper found some significance, or 2 papers showed it was not due to radiation. I think I said it was. The third paper showed that it might be. It's probably going to be a few more years before we know. I was reading up on these this summer. And so the scientific like consensus is still kind of out. All right, any questions on that stuff? Okay, that is where we're going to stop with notes today. So I'm going to stop the recording.